Hi, my name is D. Venkataraman. I'm also known as DV, short form of my name. I'm a faculty member in the Department of Chemistry here at the University of Massachusetts, Amherst. My research interest is to look at intermolecular interactions and molecular packing and how we can assemble these molecules and developing strategies on directing the molecular packing into specific structures for certain applications.
Hi, I'm Serkan Yurt. I'm a graduate student in the DV group at UMass Amherst, and my research interest is to use conjugated divalent copolymers to direct the morphology of the active layer in organic photovoltaic cells.
Hi, I am Nagarjuna and I am a graduate student in DV's group, and my research focuses on the impact of side chains on packing and charge transport in pi-conjugated organic systems.
Hi, my name is Venkataraman and I'm working in DV group and I'm a graduate student in UMass Amherst. My research interest is focusing on developing new strategies to assemble electron acceptors and electron donors into bulk heterojunction structures.
And we are all authors of a paper in the Journal of Physical Chemistry Letters looking at the role of molecular architectures in solar cells, organic solar cells. Now, organic solar cells allows us the opportunity to make flexible solar cells as opposed to what you see in silicon solar cells, which are not flexible. If you can make flexible solar cells, one can imagine making things like a backpack solar charger or a solar roof top or a solar curtain for windows. And currently, the efficiencies of these plastic solar cells are about 7% in the lab and 3% in the mass production. The silicon solar cell that you see in rooftops are about 16%. So in this paper, we argue how the molecular architecture and molecular packing affects the physics of these devices. And as we learn a lot about these connections, we'll be able to make, in the future, a 10% solar cell, plastic solar cell, which will be very good and very affordable. The work at UMass in my group is funded by the National Science Foundation Center for Chemical Innovations, Fueling the Future, the National Science Foundation Materials Research Center on Polymers, and a grant from the Army. So let us first look at the physics of the solar cell. What's the fundamental process in a solar cell? Now, in an organic solar cell, you have two components. One is an electron donor, and then another is an electron acceptor. So we represent in the structure here electron donor with the blue and electron acceptor in the orange. Now, you have electrons in the energy levels, which is the highest occupied molecular orbital, called HOMO or valence band. And when the sunlight hits that molecule, the electron in that orbital gets excited to the higher level, called the conduction band, or the lowest unoccupied molecular orbital, called LUMO. When you have that excitation, you create an empty orbital in the valence band called the hole, and electron is in the conduction band. And this excited electron-hole pair is what we call as exciton. In the next step, the electron has to now transfer to another material, in this case, the electron acceptor, and it goes to the conduction band of the acceptor. If the electron does not go there, then the electron will come back to the valence band and recombine and lose all the energy. So for the photovoltaic cell to work, you need the electron to get excited from the donor molecule and transfer to the acceptor molecule. And the acceptor molecule and the donor molecule have to transport the electron of the hole to respective electrodes to tap the energy of the electron.
Let's think that I am electron donor and my colleague is electron acceptor molecule. And so in my highest occupied molecular orbital level, I have an electron. And when I absorb light, this electron sitting on my highest occupied molecular orbital level gets excited to its my lowest unoccupied molecular orbital. And from there are two options. It can either come back to my highest occupied molecular orbital level, or after getting excited, it can be transferred to another molecule, which is electron acceptor molecule. In this case, it's NAC. And this way, we can transfer electron to the electron acceptor. And this is the energy that we gain from this process. But to be able for this process to work, the NAC has to be close by to me. And that distance has to be around 10 nanometers. If it's not 10 nanometers, what's going to happen is that once the electron gets excited, it's not going to be able to reach to the acceptor, and it's going to come back. And this way, we are going to lose the energy. It's going to be a waste of energy.
And that is the first problem, is you have a donor and you have an acceptor. And how do you bring them together in 10 nanometer distance in the molecular scale? If you don't do that, then the electron does not get transferred. That's our first problem, bringing electron, donor, and acceptor at 10 nanometer distances. Now, once the electron has been transferred, then the electron acceptor has to move the electron to the electrode, and the electron donor has to move the hole to the electrode. That's the second problem.
So here is an example where you can consider this one piece as a molecule. I have arranged all the molecules in proper order, and it is continuous. So you can think as one of the packing, and let's say the electron is, now you can see the electron moves continuously from the interface to the electrode. And here's another example where you can see all the molecules are properly stacked, but still you have some defects. And in this case, what is going to happen is, if you knock it off, the electron gets trapped or the charge gets trapped. So we call that as a charge trapping site. So we don't want this to happen. And another problem we have to worry about is how to pack all the molecules continuously and also in proper packing distance.
So we talked about two problems. One is, how do you bring molecules together close enough that they can transfer the electron? That's about 10 nanometer distance. And we also talked about how you have to arrange molecules to move the charge from the interface to the electrode. So what is a problem in getting the structures? In this paper, we talk about a lot of approaches that people have used to get the structure that we want. One main issue with these molecules is that if I take an electron donor, shown here as blue, and an electron acceptor here, the electron donors are electron rich, and electron acceptors are electron poor. Because of this, you have a very good interaction between the electron donor molecules and electron acceptor molecules. But if you remember what we said before, what you need is an arrangement like this, where you have an electron donor giving electron to the acceptor, and you need to have a proper stack of the donor and acceptor. But this interaction is a very strong interaction. As Nag will show you, how if you take an electron donor and mix it with an electron acceptor, what you'll find immediately is a color change indicating the formation of a complex between the electron donor and the electron acceptor. This is what is called a charge transfer complex. You see a darkening of the color. Okay? And that color formation indicates that there's a complex formation between the donor and the acceptor. So in my lab, what we are working on is how to avoid that interaction. And how can you make segregated stacks of donors and acceptors at the nanoscale. And the way we do it is by attaching side chains to these molecules, which we have to do because of the processability. But then, if you think more cleverly about the side chains, and if you're going to put the side chains which will not like each other, like water and oil, or Teflon and oil. So if I were to put a side chain on one molecule, let's say the accept donor, which are like oil-like, and on the acceptor, either Teflon-like or water-like, then if I were to form this complex, these side chains will not be able to mix. And you will get, hopefully, segregated structures. And we show in this paper some examples of how this strategy works. And so if you take a molecule here, which is again the same donor, but then mix it with an acceptor which adds the fluorocarbon side chains, what you will find is there will be no color change, indicating that there is no formation of the charge transfer complex. And so you do not see the color change in that case because the side chains actually will not allow the formation of the charge transfer complex. So ultimately, in order to make efficient solar cells, we have to worry a lot about how molecules pack. And we have to develop strategies of to get the molecules to pack there where we want. And we have to connect the packing of the molecules with device physics, how the packing affects the device physics, how the molecule affects device physics. By developing the understanding, we'll be able to design molecules and photovoltaic cells which are 10% or more efficient.